Hello, my name is Aditya Pandey and I'm a PhD student at the University of Illinois Urbana-Champaign. I'll be talking about my work on information field theory for Bayesian Inference in engineering that was done in collaboration with Professor Singh and Professor Gardoni.
Random fields or stochastic processes, as they are often called, are widely used to model systems that vary in space and or time, so spatial-temporal phenomena. Some of the applications from varying fields of study are depth of water in a flooded area, ground acceleration due to an earthquake, unemployment rate in an economy, or corrosion in structural elements, just to name.
Gaussian random fields are often used to approximate some of the physical phenomena mentioned before, and this is because Gaussian random fields can be completely characterized using mean and covariance, and they also have closed form solutions for conditional and marginal distributions. However, non-Gaussianity exists in many of these random fields, and capturing that could lead to more accurate analysis. Talking about analysis of random fields, Bayesian inference allows using a prior understanding in the data to update our models. For instance, under a parametric approach, when one can estimate the parameters of a model using the base formula shown below, where we have a likelihood function and a prior, and the denominator, which is often called evidence, that is calculated by integrating the numerator over all possible parameter values. Now, even for a relatively simple model with few parameters, computing evidence can be complicated. Markov chain Monte Carlo methods, they help us avoid this computation. A problem arises when the inference has to be drawn on the random field itself, so it's a non-parametric approach. The base formula can be rewritten as shown here, where instead of theta we are now using v, which is the random field itself. The denominator, which is the evidence, is now an infinite dimensional integral since v is a continuous random field, so it's a functional integral. Furthermore, when the posterior distribution is non-Gaussian, obtaining analytical form of the same gets even harder. MCMC methods can still be applied, but in that case, we would have to discretize the continuous random field. A statistical physics-based technique developed under the umbrella of information field theory provides a solution to this problem. This technique, which is referred to herein as the diagrammatic perturbation technique, provides closed-form analytical posterior moments, unlike MCMC that are numerical in nature. It works best on a perturbative continuous non-Gaussian random fields. For any discretization level, this technique provides results much faster than MCMC. We'll talk about the last 2 points in detail in the upcoming few slides.
So starting with the general framework behind IFT itself. IFT uses connections between Bayesian inference and statistical physics. A field in physics is any physical quantity that is defined on all points in space, with each location having a set of possible values, so which is very similar to the definition of the random field itself. They have a term called Hamiltonian, which is a key construction which corresponds to the energy associated with each configuration of the field. Now, the probability that the field will have a certain configuration is given by this equation shown here, which is very similar to the Bayes theorem equation, where the denominator z, partition function, that is obtained by integrating the numerator over all possible random field values or the field values.
The similarity between Bayes formula and the probability of field configuration that we saw in the last slide is used to define the Hamiltonian for a random field as a negative natural log of the joint distribution, and the partition function is defined as the integral of the negative log of joint plus an additional term over all field configurations, where the additional term has the coefficient j, which is a bookkeeping variable. The partition function, it also acts as a moment generating function, because if we take the nth derivative of this function, we get the nth order posterior moment. So ideally, knowing this partition function would be helpful in estimating posterior moments, but it has the same issue as evidence had, that there is no analytical solution for non-Gaussian random fields. So expanding the Hamiltonian reveals some patterns. The Taylor expansion of a generic Hamiltonian has some Gaussian terms, since a negative log of a Gaussian distribution would give us up to second order terms. So the first three terms are called Gaussian terms. And then there's a higher order terms written inside the summation, which are called interaction terms, since v to the power n is like the interaction of the random field values at n different coordinates. You would notice in this particular equation, as well as in all the upcoming mathematical expressions, that for brevity in equation or in expression, we are using same terms for both discrete and continuous cases. In discrete case, they would be denoting a vector product, whereas in continuous cases, they are representing integral. So the partition function of a Gaussian Hamiltonian, which uses only the first three terms, has closed form solution as shown in below, which is only a function of capital J, little j, and d. And this is something that will be helpful for us in the non-Gaussian case.
Now the non-Gaussian case can be written as an extension of the Gaussian case that we saw before. By solving the partition function expression for a non-Gaussian case, we notice that it comes out to be an operation of the interaction Hamiltonian on the Gaussian partition function for which we have a closed form. So then performing a Taylor expansion on this expression, we notice that it yields a sum of infinite terms, but each one of these terms has a pattern as shown below. And in the expression below has these coefficients or these exponents a, b, c, e, and n. All of these are integers with well-defined relationship between each other.
So if we can come up with a system that keeps track of all the terms in the infinite summation of the partition function, that can help us in estimating the posterior moments. One such system was developed by Richard Feynman. Recall that the terms such as J transpose dj are integral of values over coordinates in an infinite dimensional continuous random field case, as shown in this expression below. In this integral, you can think of the function capital J and little j as nodes at coordinates x1 and x2, and the function d as the line connecting these two nodes x1 and x2. Similarly, the interaction coefficients that we saw in the expansion of the Hamiltonian, that are vertices with edges. Using these rules, a term such as J transpose dj can then be drawn into a diagram where we have a dot representing capital J, a line representing j, and a cross representing little j.
The contribution of each diagram, such diagram that we saw before, to the posterior moment is obtained through the partition function. Recall that by taking the nth derivative of the partition function, we got nth order moment. Therefore, diagrammatically, taking derivative with respect to capital J is equivalent to removal or freeing of a node in the diagram. For instance, if we took the derivative of J transpose dj with respect to capital J, we get the expression dj, and equivalently in terms of diagram, it is equivalent to removing the left hand side node that we saw in the previous slide or freeing of the left node. This also implies that nth order moment, or which is equivalent to taking n derivatives of the partition function, will have n free nodes in a diagram. So following these rules, we can get diagrams as shown below. On the left hand side table, we have the first four diagrams that contribute to the posterior mean, and on the right hand side, we have the first four diagrams that contribute to posterior covariance. And we notice, for instance, looking at the first figure, we have two ends or two nodes in this diagram. Each one of each vertex or each node corresponds to a coordinate, and this particular diagram can be translated into a mathematical expression as d, which is a function of x and y coordinate, and j, which is a function of y. So similarly, we can obtain the mathematical expression for each one of these diagrams.
So sum of finite number of diagrams could provide an approximation of posterior moments. For this approximation to be accurate, the non-Gaussian case needs to be perturbative. That is, the higher order terms in the Hamiltonian, they need to converge to zero, as we saw in the expansion of the Hamiltonian, which implies that the Hamiltonian can now be written as a sum of finite terms or finite diagrams. Often, this perturbative characteristics can be obtained by using a weakly informative prior, which is not always the case, but this is one way of achieving perturbative non-Gaussianity. In such perturbative cases, the posterior moments can be approximated as sum of finite diagrams, as shown in the case of posterior mean, and each of these diagrams can be translated into corresponding mathematical expressions.
To use this technique, following steps can be followed. We can start by identifying the prior and the likelihood. We can write down the Hamiltonian in its expanded form to obtain the expressions for capital D, little j, and the interaction coefficients lambda. We can check if the higher order diagrams converge to zero or not, since that could be indicating whether the Hamiltonian is perturbative or not. We can identify the desired accuracy and the corresponding number of diagrams by using the library provided in Pandey et al. 2022. And using these diagrams, and we can check if the mathematical value for each one of these diagrams is decreasing with the increasing order or not. If it is, then the sum of mathematical expressions of a finite number of such diagrams can give us the posterior moments. As an example, we applied this to a case where we have both Poisson and gamma likelihoods just to demonstrate the perturbative nature and applicability. So as an application of this IFT, this is demonstrated through a case of non-homogeneous Poisson process. It is assumed that both discrete and continuous data is available from this point process. The discrete data, which is represented as d sub p, can be count of occurrences of events represented using Poisson likelihood. And the continuous data can be the time to a certain number of occurrences or any other observation model through gamma likelihood. Both data types are related to an underlying rate factor, that is the continuous random field V. And the relationship between rate factor mu and the random field V is given using this equation. The goal here is to use a finite number of observations of either discrete or continuous data to infer the rate random field. For this example, we have assumed a Gaussian prior for the random field. However, this assumption is not a requirement. One can start with a non-Gaussian random field prior as well. So the next step is to identify or expand the Hamiltonian for both Poisson and gamma case so that we can identify the expressions for capital D, J, and interaction coefficients. So we start with the Poisson case, where the Poisson likelihood is given as shown here, assuming that the I data points or the n data points are independent of each other. So the count occurrences that we see in each grid cell of the domain, those are independent of each other. We use this likelihood with the Gaussian prior to get the Hamiltonian, and this Hamiltonian reveals that the expressions for capital D, J, and lambda are as shown in this box, and this is the most important part of this entire exercise. We repeat the gamma likelihood case. We write down the gamma likelihood, combine it with the Gaussian prior, and that results in the expressions for capital D, J, and lambda. So we used these three terms for both Poisson and gamma along with a. So to create a perturbative non-Gaussian theoretical case, we use the following numbers for unknown variables. For the mean and standard deviation of the Gaussian prior, we use 0.5. For the coefficients b and k in the rate factor expression seen previously, we use 0.9 and 1. And then we also assume that the domain of the random field is between 1 and 10. Using a scenario random field with these parameters, we generated gamma and Poisson data, and then we use this data to infer the posterior moments for the random field. And we observed that with both IFT and MCMC, we get similar results. And also when we compare the runtime of IFT with that of MCMC, we see that IFT, being an analytical approach, is several times faster than MCMC. So to conclude, a parametric approximation of random fields with any known distribution such as Gaussian, along with inference on a finite number of parameters, is one way of addressing the issue of Bayesian inference on continuous random fields. MCMC methods offer another way of numerically approximating posterior. However, these methods either provide inaccurate estimates due to distribution approximation or grid discretization, or they are completely computationally expensive. We demonstrated a method from the field of information field theory that we call the diagrammatic perturbative approach that allows expressing posterior moments as a sum of diagrams. This technique is used on a non-homogeneous Poisson process case with either Poisson or gamma data, and we are currently working on expanding its applicability to non-perturbative random fields as well. Thank you.